Welcome to part 2 of our plate tectonics review. In the previous video, we went over, a lot of stuff. Earth's layers and the system for layering, what we mean by plate tectonics versus a tectonic plate, a lot about Alfred Wegener, but also started into plate tectonics travels. That in California, the plates are sliding by, giving earthquakes. That's called a transform boundary. In Iceland, the plates are pulling away. That's called a divergent boundary. But now we're at Mount Everest, the tallest peak in the world, about 5 miles high for this peak. Well, what could possibly be going on with the plates there to cause this? Here is a model that students created of it. Now, it's a little funny at the top. You see some wild creatures, some mountain climbers. But what I want you to notice is, it's kind of small. These are 2 arrows pushing together. It's a convergent boundary, but it's a special convergent boundary. The type of crust hitting, notice that they're both green, meaning that they're showing continental crust. So continental crust pushing together, continental convergent. Trick question, what sinks? You should be thinking nothing, because same crust type, same density, building mountains. Now if I was going to, I'll just do it. I'm going to draw this little fish. A happy but fossilized fish up there. The reason I'm drawing that is evidence that this is the plate tectonic situation is that there are oceanic fossils up at the top, meaning ocean crust was thrust all the way up there. Interesting little fact. Okay, now we're getting to volcano stuff because we went to Hawaii and then Japan to finish our travels. And when you see this, you should be thinking of a special molecule, and the charades I've done with you with this is like that. This molecule's name, of course, is silica. Now, these are 2 different pictures of it. This is what pure silica looks like in mineral form. But this picture shows, if we can get down to the molecular level and look at the way the molecules fit, because the individual molecules are hexagon shaped and they have 6 flat surfaces, they tend to fit together tightly. Now that's important because if you have lots of silica in your magma, does it flow easily or does it resist? High silica, you should think resisting flow. If it has not much silica, the molecules don't fit as tightly and it can flow easily. Okay, so now let's check these 2 out. The question at the top is, which of these eruptions would you consider non-explosive? Okay, so look at the differences. Okay, you should be thinking, Ms. Fickus, the non-explosive is A. Non-explosive because lava flows. You might look at that and think ash. Not actually ash, that would be steam, water vapor coming out. Over here you see volcanic ash, which is a type of pyroclastic material. Probably there are little chunks of rock being thrown out also, instead of just pulverized slivers of rock. This is our non-explosive. Okay, now, if I say this is our non-explosive, which one of these 2 would have magma inside that's low in silica? Okay, low in silica, your answer would be A. Over here, in this picture, the magma inside the volcanic mountain, which is blocked out by the ash now, the magma would have been high in silica. That high amount of silica within this mountain is like the black stopper on our volcanoes. It would clog the vent, pressure builds, bam, and all of this ash is actually pulverized rock from the inside of the magma chamber. Okay, so now we look at these 2 different mountains, Mount St. Helens and Mauna Loa. This is the Hawaiian one. How come it's wide and flatter? Low silica magma, runny lava flow, low viscosity lava flow, doesn't resist flow, and that's why you get its shape. Mount St. Helens erupts explosively, giving you this steeper peak. This is the same as Mount Fuji in its shape. Okay, so in Hawaii, we have a weird plate tectonic situation. And when I say weird plate tectonics, here's what you should be thinking. Our other 4 locations are on a boundary, but Hawaii is in the middle of a plate. And so what's the deal? Notice that this says it's a fixed hot spot, which is just a weakness in the crust there that magma gets out. But there is movement of something, and that thing that's moving is the plate. So during a period of high eruption, high lava flow, you get these islands. Now in between here, the plate keeps moving, but the eruption rate is not as high, and so you don't get an island to pop out. Actually, in the spaces between, you might remember us talking about there are little mountains that just don't pop up. But Hawaii is in the middle of a plate. Now, when you look at this, and you see that this is the Pacific plate, this is oceanic crust that would be low in silica. So the oceanic crust is getting melted, and this low silica magma is coming out that's just able to flow. Okay, now check out this one. This is actually from a student a few years ago. This is the best model I've seen that shows the formation of Hawaii. When you look up here, these clay splotches are the different, actually the different islands, the hot spot here, and they could physically take and move this. Now you might think, Ms. Fickus, what's the deal? There's only one arrow. Why wouldn't there be two? Remember, this is in the middle of a plate, not a boundary. So there aren't two plates interacting, just the movement of this one plate over a stationary, fixed-in-place hotspot. Okay, well there it is, Mount Fuji, also from the sky. This one is not a shield volcano like Hawaii. This is a stratovolcano, also called composite. That's how it erupts explosively. Now, what is our reasoning for that? Here it is. This is a subduction zone. So you notice that oceanic crust and continental crust are meeting. This side is the continental, that's the oceanic. Now, what's happening to the oceanic crust? It's sinking. And in this area, if the oceanic crust could sing, it would sing this song. It's getting hot in here. I'm turning into magma. Okay, so this part is the subduction zone. This is the plate tectonic situation in Japan. It's a continental oceanic convergent boundary where you have the oceanic crust sinking because it's a greater density made of more dense minerals melting into magma. Now, how come it's explosive? As you see this oceanic crust that gets melted come up, it's coming up through continental crust. Continental crust is high in silica, so you end up getting high amounts of silica in this magma. Now, some of you are probably looking at this little drawing, and hopefully you're picturing that black rubber stopper. The thick, high viscosity magma with lots of silica clogs the vent till pressure builds, then bam, an explosive eruption with an ash column. So this is the situation in Japan, a continental oceanic convergent boundary. So, I think that's it. I think that's your main stuff. Thanks for watching the video, and best wishes on your test. Wait, Mr. Fickus is Mr. Fickus pointed at me. He is recording this, and he's like, you forgot something, and I did. This is one of the best models I've ever seen made of a subduction zone of the continental. You can see a little green here. Continental crust hitting oceanic crust, sinking, turning into magma. Pressure builds, and then the only little issue is it almost looks like magma or lava coming out. That would really be a volcanic ash column there at the top. So, good luck on your test. Thanks for watching.